Hello everybody again, and today we are going to discuss group codes, how to design a group code, how to uh, test group code operation, how it performs error correction in multiple scenarios, and accordingly uh, finalize it by creating a schematic of the devices that perform coding and decoding operations. So we'll start with some mathematical background to get acquainted as to what exactly is a group, why this code is called group code, and so on. So also let me turn on the chat if you have any questions to see. So basically, as I have told you last week, Shannon proposed a rather not so simple approach to making the codes by selecting manually code words. Some of them are marked as allowed code words, and other ones are restricted ones, and you have to organize multiple subgroups. For example, you have subgroup with some allowed code word and multiple restricted ones, yes. And you have to manually pick up the code words to actually make it efficient. So, as I said, later, after Shannon proved the potential possibility of sending data without errors by correcting some of the errors, multiple scientists have started working on some mathematics behind this coding, and accordingly the coding theory has emerged, and some mathematically designed codes are now available for us to be used. So the basis for the mathematics in this coding theory is mostly linear algebra. It uses vector spaces, it uses matrix, and it uses group theory. And now we'll talk about what exactly are groups, what are different algebraic systems which we are using, because in cyclic codes we are going to use some another terms called field. Yeah, so this is also mathematical, well, we can say construction, yes. So I'd like you to get some more information before we go further about what are these so-called algebraic systems. So each code word can be represented as a decimal number. Yes, for example, if we have this code word, then we can actually consider it to be a binary number. Yes, and convert it into any other base. So in this particular case, this code word of 7 binary symbols can be considered to be a number 105 in decimal form. You can also use octal form, hexadecimal form, and so forth. But what matters here the most that actually each code word is, in a sense, just a number. Yes, very similar to numbers we are using in our decimal system in our daily life when we add numbers, we subtract numbers, and so forth and so on. So some similar operations should be possible to be done with the code words. So let us start by defining what is actually some algebraic structure. So you may already know that there are sets of numbers of, for example, natural numbers starting from 1 and up to infinity, some integer numbers. Yes, each of them has its own notation. So we often write, for example, x belongs to, for example, z, where z is integer numbers set. Yes, so this is a mathematical set of the numbers, including all the elements that are matching some condition. And in our particular case, the condition is having a zero fractional part. Yes, so this is just a set of numbers, but this is not yet algebraic structure. if we add to this set of numbers some algebraic operations such as adding, subtracting, and so forth, then we get algebraic structure. So basically this is still the set of numbers, however it has also specified some mathematical laws in which we can assign to some two components of this set, so both I and j component belong to this set of numbers A, and as a result of this algebraic operation, we get some kth component, which also belongs to this set of number. So this is strictly defined assignment ways, meaning that each time we perform this operation with these two set members, we always get the same result. It's not a random, it's predefined. Yes, exactly like, for example, you have integer number 2, you add integer number 3, and you get also integer number 5. And it's always the same result of the operation because this is basically a mathematical law which we have defined ourselves. So this basic operation, algebraic operation, can be very different. It can even be something we haven't designed yet. Yes, we can describe this operation and accordingly use it later on. But again, in a sense of equivalent decimal system, we can consider this to be adding, subtracting, dividing, multiplying, and so forth. Yes. So algebraic operations can be direct and inverse. So for direct operations, we have addition and multiplication. And you might recall that somewhere in the first, second form of the beginner school, you may have learned adding and then describe subtraction as opposite operation to the adding. So for example, this difference means to find ai, yes, such that adding it to AG would actually produce AK. So basically you have some testing load for this subtraction. So this subtraction is not defined as direct operation. It relies on this addition. Similarly, division relies on multiplication. That is why they are called inverse, and these are called direct operations. So let us, here you can also look more about theory part. Okay, this link is no longer available. I will find up was wrong, but it was working yesterday, I believe. Okay, well, I will give you after the break the correct link. I will find this guide. I have it somewhere, and we'll find a new link. So let us define what is a group, and the group will be accordingly the main algebraic structure based on which a so-called group codes are designed. So this is some specific mathematical term rather than a simple description of some set of components. Yes, so as we said, the group is algebraic structure, so that means it has some set of numbers. In our particular case, it's code words represented in binary form, and some operations. So the group has only one direct operation defined, and accordingly additional properties which are listed below. So the selected operation is associative. That means that the order in which we perform this operation is not relevant. Well, this is often true, yes, for our decimal numbers. However, you need to understand that this doesn't necessarily is obvious, yes. So there may be examples of operations where the order actually matters, yes. So in this particular case we are discussing, the multiplication or addition is indeed well associative and doesn't matter. So it's not really relevant if we add up like this, for example, or add up like this. The result will be the same, and it's 12. Yes, in both cases. Also, another important property, that there should be some identity element E, so that the result of performing this operation, which in this particular case can be any operation, yes, doesn't change result. So if we are talking about addition, then the identity element is actually called 0. So you add 0 to any element and the result is maintained. Yes. If we are talking about multiplication, the identity element is called 1. Yes, because multiplying with 1 doesn't change anything. So this is A. Yes. So depending on the selected operation, the identity element can even have a different name. Yes, this is called 0, this is called 1. So for also additional property, for each of the set elements, there should exist inverse element, so that performing operation between direct and inverse elements gives us actually this identity element. So for multiplication, so for addition, again, that would mean that each element has opposite sign, yes, because this way we indeed would get 0. And for multiplication, the element has to be inverse fraction. Yes, so basically inverse element would look like this. And as a result, we get 1, considering that A is not equal 0. Yes. So these are three main properties which needs to be basically true, yes, in order for the set with some single operations to be considered a group. So for binary operations, we are not going to use the common sense addition as usual. So basically addition produces us components, yes, for example, 2 plus 3 to be equal 5. And for binary operations, we would like to be in limits of 1 and 0. So basically, if we use classical addition for 1 plus 1, we would get 2, which is not what we want. We want to stay in these two numbers, yes. So for that reason, we are going to use rather XOR operation, which can be considered to be addition by using modulus 2. So that means that we add numbers together, divide them by 2, and as a result take a remainder. And this gives us such a truth table which we desire. Yes, so all the results are also belonging to the set of numbers 1 or 0. So in such case, it's important to note that automatically we have inverse elements as well, because adding up the same numbers would produce always a 0. That is the logic of the exclusive OR, because exclusive OR always gives the result 0 when we have same inputs. Yes, two same inputs give always 0, and accordingly 1 if the inputs are different. So that means that this automatically, by choosing this basic operation, yes, this algebraic operation, direct operation, automatically takes care of us for this third property, and it's always true. Because naturally, if you have, for example, such a code word, for example, yes, then you add by exclusive OR the same code word to itself. As a result, you would get 0 element. Yes. So the third property is maintained automatically by selecting specific operation which is suited for our binary data. Again, so some short example. We have three, let us say, candidates to be a group, and accordingly, the base operation is selected to be XOR. So which of these sets, so these are sets of numbers, but are they necessarily group or are they not a group? So how do we check that? First of all, we need to make sure that we always get as a result of some operation between these two set members. So for example, let us take this and this. So we need to make sure that any pair would produce us the result which also belongs to this set of numbers. So basically I add them together by XOR, and what I get is 0, 1, 1, 1, which is true. It belongs here. However, if I now check first and last one, these two, yes, add them up together, then I would get the element which is not listed in this list. So this cannot be true for group. So the answer for this is no, because it doesn't include all possible elements, yes, which can be obtained by performing base operation with any pair of these two elements. Besides, it also doesn't include zero element. Yes, there is no such element as zero, because if we take any component and add it up by itself, we should get zeros, which should also be listed here, but they are not. So for the first candidate, the answer is no, it's not a group. However, it is a set of numbers. It has algebraic operation defined, but it doesn't meet all the requirements to be a group. So for the second one, we can see that we have zero element. However, the story is the same. If we choose two elements, they should always produce the result also belonging to this group. So let us add these together. And we can see that the result is not listed in this set. Yes, so basically that means this is also not a group. So in order to prove that it is actually a group, you have to perform operation between each pair. In order to prove that it's not a group, it's sufficient to mention at least one example when the property doesn't hold true. Yes. So in this case, I have found this pair which produces a result which is not listed. Accordingly, this means that I have proven that it doesn't meet the criteria of being complete. Yes, it's not complete. And accordingly, this is not a group. So for the last one, we need to be more specific to check all the requirements. So because here we have three binary symbol combinations, all the possible combinations starting from 0, 0, 0 and ending by 1, 1, 1, without skipping anything. So there are total 1, 2, 3, 4, 6, 7, 6, 7, 8. Yes. So there are total 8 combinations, meaning that all the possible combinations we can make from ones and zeros in 3 digits are listed here. So this is complete. You will never find a pair here which produces some result which is different, considering we have XOR operation. If we would use classical adding, for example, without modulus 2 like this, then sure, we would get result which is 1, 1 here and carry bit here. Yes, that would be beyond 3 bits. So for classical addition, but for XOR, we always are going to get one of these 8 numbers by performing operation with any number of these other numbers. So it's complete. It has 0. Yes, so this property is true. Obviously, it's not important in which order we add. So basically, do we add it like this? Or do we add it like this? As long as we add the same numbers, it's not really relevant in which order we do it. So in both the cases, we get zeros. And also each element is inverse to itself. Yes, so it looks like all the criteria are met and this is a group. So the answer here is yes, this is a group. So hopefully now you understand what are the requirements for the set to be called a group. And as you imagine, most probably when we design a group code, then the set all the combinations will be a group. And that is indeed true. But let us go further. It turns out that in this group, which we have proven now to be a complete group, we can select a subgroup. So for this subgroup, all the requirements are still the same, meaning that you cannot have any, well, for example, if we check now all the possible additions, then we always get a result which is also listed in this set. Yes, so here we get these. Now, if we add 0, 0, 1, and 1, 1 this way, we would get this combination. And what is left, we also need to check this. Well, I'm not checking for zeros because obviously zeros don't change anything. Yes, that is the property of this zero element, which is called identity element. Yes, in general case. In addition case, this is called zero. Yes, and well, it doesn't change the result, so I'm not testing it by adding to each of them. So in all the cases, we get something which belongs to this subgroup. Yes, we didn't get anything new. And all the possible combinations of adding have been tested in this particular case. Well, I'm not changing order, yes, because it's associative. It doesn't matter in which order we add these numbers. However, here I'd like to mention that not always the operation is associative automatically. This is especially true, for example, for matrices. Yes, so consider that you can that you have, for example, this matrix, which is represented by a row vector, and you multiply it with a vector column. If you change the order of these elements, then you will not be able to calculate it. Well, so let us calculate. So that would be 10 plus 18 plus 28. So that would give us 28 plus 28, which is 56. Yes, the result of this operation. Now, if we change the order, we cannot calculate anymore this result. Well, we can, but it will be different result. Yes. Now, I mean, let us launch Octave. It will be faster. As a result, so that would be 5, 6, 7 as a column, A. B would be 2, 3, and 4 as a row. And if we multiply A with B, we get entire matrix. Yes. The answer will be different. And this means that matrix multiplication is not associative operation. Yes. So this is example that it doesn't mean like it's always automatically also associative. In some particular cases, some operations can be not really associative. So we have to make sure that this is associative. For our case, XOR operation with binary numbers is associative automatically, yes. But, well, as I said, sometimes it can be not true. So subgroup is important definition because it will turn out that all the allowed code words are actually a subgroup inside the group of all the possible code words. So allowed code words are also a group, and that's why the group codes are called group codes, yes? So all the possible code words form a group. So if we have a code word with length m, that would produce us in total 2 at the power of m code words. So let us take, for example, 7-4 code, meaning that we have 7 total bits. So C1, C2, C3, C4, and of these 7, 4 are information bits. So other are control bits, E1, E2, and E3. Yes, so 7 in total, and 4 of them are information. So that would give us total number of combinations in this particular case 128, because m is equal 7. And these 128 possible combinations starting from 7 zeros and ending with 7 ones are all possible code words, including allowed and restricted alike, yes? So if we are talking about only allowed code words, then they form a so-called subgroup in this group. And the size of this subgroup would be, accordingly, 2 at the power of k, which is 16. So we already discussed that in previous week lecture. And what matters the most is that you don't have to select them manually. They are automatically forming a subgroup, and you only need to define this subgroup, and that's it. Yes, so no need to select manually code words which are allowed and which are restricted. Allowed code words automatically with this theory form a subgroup. So base operation is XOR, code word length is m, and number of information symbols is k. Accordingly, the number of control symbols will be further denoted by R in all the lectures we'll be having until the end of the year. So this notation will be kept. Yes, M is total, K is information, R is control symbols, number of these control symbols. So that is for group code. Yes, so here we are going to stop for now, but there are other mathematical structures. As I said, I will show you after we have break a link where you can read more. Yes, but to mention, there are actually not only groups but also rings. So basically, ring is different from a group in a sense that it has 2 operations. So if group can be based on multiplication or addition, then ring necessarily has both addition and multiplication. So 2 operations. Accordingly, it should have basically 0 element. Not mandatory to have 1 element. Also, there is additional requirement that A multiplied with B plus C should be possible to calculate like this. Plus C, yes. And this is called distributive flow. And I believe basically that's it. So it's still a group with some additional properties. Yes, so it's based on group, but we add one more operation, one more condition. Yes, and that's it. Yes. Also, the ring can be commutative. In that case, we have to have one. And this is base for next level, which is called field. Yes, and the field will be the base for cyclic codes theory. Cyclic codes theory. But we will get to the field a bit later when we'll talk about cyclic codes. For now, we'll stop here and we'll continue talking about group code. Yes, because too much mathematics, and this is actually not a simple mathematics. Yes, so I don't really want to spend entire lecture for the mathematics. Let us maybe continue talking about group code. So the allowed code word is generated from information. So the idea is that you have some information to be sent, and you are using this information to determine control symbols, yes, which you are later adding at the end or in some other positions, not really necessarily at the end of the information block. So what do we need to know to be able to calculate these control symbols from these information symbols? First of all, we need to know how many of control symbols do we need to be able to correct specific number of errors. So in our particular case with 7.4 code, which can correct only one error, we need to provide for 4 information symbols 3 control symbols. In that case, any single error can be corrected, regardless of position where it happens. Then we need to actually calculate these check symbols and append them to our information symbols. Then this results in code word, which is accordingly sent in the channel. Later, we have a noise added to our signal, which leads to incorrect detection of our signal and accordingly some possible errors in our code word. So, how do we know how many control symbols do we need? Well, in particular, we need to consider all the possible error combinations. So we call the error vector such a vector which shows by symbol 1 where error is happening. Yes, so for example, this is error vector for the error in the first symbol position. So in the first symbol is 1, all the others are 0. So this is some sort of mask which we are adding to our information or control symbols. So basically E1, E2, E3, and we add it to our code word. Accordingly, after adding, this is inverted, and all the other symbols are the same as before. And this is how we introduce this error mathematically in our models, in our simulations, in your calculations in course project, and so forth, just by inverting the specific symbol. So in this case, we invert the first symbol. For the second error vector, we invert the second symbol, and we go through all the possible positions, yes, including control symbols, because if the error has happened in control symbol, we also need to know about that and be able to correct it if it's necessary. It's true, however, that in most cases we are not interested after receiving data and checking for errors in these control symbols anymore, and we often discard them, but we still need to be aware that during the transmission, the error that has happened is just the error in this control symbol. Yes, so we include these error symbol positions as well as the possibility of the error place. And in order to be able to detect the error, we need to have unique syndrome for each error. So the similar way as each illness has some symptoms, yes, the similar way each error should produce specific syndrome. For example, in this particular case, we assign syndromes just in a regular order. So this is 1, 2, 3, 4, 5, 6, 7 in binary form, yes. So we are just denoting the position of the error, yes. So this is first position and this is seventh position. That is simple. And we automatically can see how many bits for the control symbols do we need, because number of bits in syndrome and number of binary symbols in control bits in code word is the same. So that gives us automatically R is equal to 3. So in your particular case, when we discuss your course project, that means you have to start with the error vector table. So consider you have, for example, m equal to, I don't know, 17, for example. That would mean that you need to start making this table. Yes, 1 and then 16 zeros. 3, 4, 1, 2, 3, 4. And go further by shifting this one symbol accordingly, position after position. Yes, I am not going to write all these zeros. There will be a total of 17 such lines, and accordingly you will assign numbers starting from 1 to 17. So that would be 0, 0, 0, 0, 0, because I know that 16 is this number, and 17 will be this number. So you will need, if you have m equal 17, you will need to select 5 of these 17 symbols to be control symbols, and accordingly information symbols will be m minus r, which would be 17 minus 5, which is 12 symbols, yes, for information part. But we will derive a specific formula so that you will know that beforehand, even before you make this table. You will still need to make this table to design a code, yes, so that will be necessary. So the number of possible control symbols needs to be big enough to produce all the possible syndromes. The trick here to identify the error is actually provide unique syndromes. Yes, so each error vector should have a different syndrome. You can also include error vectors which have 2 errors. Yes, for example, like this in this table. And one more 0, yes. For example, here we can include it. And all the possible combinations of 2 errors. But we will need to produce extra syndromes for that. For example, like this. And this means that now we are going to need 4 symbols. And even more, if you take into consideration how many possible combinations of 2 errors can we make, yes, it will require you even 5 bits to be able to assign unique syndrome to each of the possible error vector. Yes, but we'll not go this far because such codes are much more complicated and have larger amount of work to be done. In this course, we are looking at the basics, yes, and for basics, a group code which is correcting only a single error is completely sufficient to understand logic of how this code is generated, how it's designed in schematic, and so on and so forth. So, as I said, each error vector needs a different, a unique syndrome. So therefore, it's possible to specify the minimum number of check symbols as a formula. Yes. Why do we add here +1? It would be completely understandable if we just take our m, which is here, yes, and calculate log 2 of the m. However, you need to understand that there is a situation when we do not have any errors, yes, and we need a unique syndrome for that too, yes. So no errors usually has a syndrome 0, 0, 0. Yes, so basically this shows that there are no errors. And we add this 0, 0, 0, the case for no errors, into equation as extra one combination. Yes, so if we have m equal to 7, then according to this formula, we get r is equal to 3, which is true. Yes, this case. So basically you can use this formula to get the number of control symbols for your specific case. For example, if you have, I don't know, m equal to 31, then putting that into this formula will produce you of 32, 5. If you have m equal 20, then you put that +1 into this formula, you would get 4 point something, I don't know, 4.7 for example, and you need to round this number up to the closest larger one. So basically perform a sale operation, which would give you 5, because you cannot really make 0.7 bits, as you already know that from information theory, to the binary symbol. You are going to use all of them. So this is a nice example if, for example, I will be limited by 5. Yes, so that will be m equal 5. And consider that I don't have this. Can I use 2 r equal to? The answer is no, because if we have r equal to, that would give us 0, 0, 0, 1, 1, 0, and 1, 1. 0, 0 is reserved for case without errors, and these syndromes accordingly allow us only to number for m equal 3, no more than that. Yes, but we need extra 2 syndromes to find errors in all the 5 places. So yes, if m is 5, then our logarithm of 6 is 2 point something, but we round that to the closest larger integer, which is 3. So you always take integer number which is not smaller than logarithm of the number of the symbols +1. Yes. So this takes care of the number of the error correct of the control symbols, check symbols. Yes. However, we still need to find how exactly are we going to calculate them. What is E1, what is E2, and what is E3? How they are obtained from this C1, C2, C3, and C4. We have to do some operations with these symbols to get these control bits. So, yes, this is some summary. Yes, basically the formula that we have to choose r as an integer number which is greater on or equal to this logarithm. And now we are going to talk about one more case. If we have double error corrections, yes, for example, considering double error corrections, then we need to actually include in formula case for one error, which is number of combinations of how we can combine one error position. Yes, so basically we have zeros and ones, and we set 1 into the specific places. So the total number of these combinations, yes, arrangements, is actually in combinatorics calculated as this number of combinations. This is number of possible combinations of having 2 errors, yes. And this is the case when we don't have any errors. So for example, if the m is 7, yes, then it's possible to have 1 error in 7 different ways, and it's possible to have 2 errors in 21 different ways. Yes, therefore, accordingly, I'm not writing all the possible error vectors of the 2 errors. So in total, that gives 28 possible ways to have 1 error, either not 1, but 1 or 2 errors. So yes, have multiple errors in this code of 7, and accordingly, that means plus extra 1, yes. So logarithm of 29, the closest larger integer is 5, and that means that out of these 7 code word symbols, 5 will be for control, and only 2 will be for information. So you have 2 information symbols, you add 5 control symbols, and this way you can protect from 2 errors. So as you can see, redundancy here is rather large, and well, design of such code is also not so simple. Anyway, let's start with our group code, and as you have mentioned in maybe as you have noticed in your course project task, this code can be systematic or non-systematic. What is the difference? We'll discuss today both of them. So the difference is the order of the symbols. Yes, for systematic code, as we have already mentioned that in last week lecture, in systematic code you have information symbols in original order. Then after information symbols, you have control symbols. So this is called systematic code word. Accordingly, if this doesn't hold true, this will be non-systematic. For example, in this particular case, for group code, non-systematic code word would look like this. Yes, we have symbol, control symbol 1, control symbol 2, information symbol 1, control symbol 3, information symbol 2, information symbol 3, information symbol 4, control symbol 4, information symbol 5, and so forth. So this is called non-systematic code word, and this was called accordingly systematic. That is basically all the difference, the order of the symbols. Now you may ask, why do we even make this not so obvious combination of symbols? Actually, there is a law. Where do we put these symbols? So this is position 2 at power of 0. This is the position 2 at the power of 1. This is position 2 at the power of 2, which is 4. This is accordingly 8. And it's possible to tell where will be next one. It will be at the position 16. Yes. So we place control symbols at the positions of the 2 at the power of some integer. Yes. Because they have syndromes like this. Yes. So this is syndrome 1. This is syndrome for the second control symbol, and this is syndrome for the last control symbol. You will see later from deriving the equations why it's so important, but generally speaking, if we use this approach, then if we have syndrome, for example, I don't know, syndrome like this, which is in decimal form 3, then this syndrome will actually tell us that the error is in the third symbol. This will work only for non-systematic code. For systematic code, the error will be in first symbol. However, the syndrome is 3, yes, so it's not so simple to find that error. We'll have to, well, you'll see when we'll work on our code, yes, for simulation for task 6, you will have additional hassle, extra code to actually find the correct position. Well, I'm going to tell you that in advance, yes, that we are actually going to convert systematic code into non-systematic code just because of this fact that it's simpler to correct the errors in that. But still, the systematic code may be more convenient for you to design logic of your communication system, because here you can see information part. It may be even simpler for communication system itself to actually extract information from the code word, knowing that you have just to discard last 3 bits and keep the rest. Yes, we'll talk about how to make it better. Yes. So for having group code, in non-systematic case, the syndrome shows directly the position of error. So for example, if we have error in the third symbol here, the syndrome will be 3 in decimal form. Yes, this is very convenient, and that is why actually this non-systematic code word type actually exists and is quite used. Yes, so this justifies this, well, not so obvious at the first sight, but nevertheless strictly mathematical order of arranging symbols. Yes, so it's convenient. Yes, it's basically talking about convenience of convenient error correction. If we know that we have error in the third symbol, we can just reverse it. Yes, and that's it. This way we have corrected the error, and the code has helped us to do it. So how do we know then the coding and decoding law? Because currently we are only talking about some general rules that we have table of the syndromes. Well, basically it's next slide. Yes, we have table of the error vectors and according syndromes. But we haven't yet talked about how does decoder know what is the error vector. So basically we have to define syndrome, yes, and then we know the error vector which we can add to our code word. For example, in last case, we have somehow, we are not talking about it right now how exactly, but we have found out somehow that the syndrome of the code word which we received, which was this, is actually this syndrome. Then we know that the error vector for this syndrome is actually this one. So we take this error vector, add it to our received code word, which is now definitely with error. And by adding this error vector, we correct our error. But the question still is, how did we find this syndrome? Yes, where it comes from, and how do we know that the syndrome is this? How this syndrome, for example, if we are going to have the same code word with error in different position, so for example, here we'll have 0, which will be error position, yes, 0, 1, 0, how this will produce us another syndrome, which would be 1, 0, 0. So how do we find from this code word this syndrome? Well, it's obvious for us because we know that here is the error and we only take number 4, convert it into binary form, and that's it. But the receiver doesn't know is this symbol with error or not. Its task is to actually find if there is an error, and if there is an error, try to correct it. So we need coding and decoding law. Yes, coding equations and decoding equations. Decoding equations. So this way, coding equations will actually tell us how to calculate control symbols, whereas decoding equations will tell us how to calculate syndrome symbols. Syndrome 1, syndrome 2, and syndrome 3. So if we will have the sets of equations for coding and decoding, then we'll have mathematical tool which allows us to take our code word and find out the syndrome. The syndrome can also be 0, 0, 0 if there are no errors. So let us start with some code word that has m symbols. M equals 7 in our particular case. And accordingly, make a table of error vectors, yes, starting from error in the first position and ending with error in the last position, and assigning in decimal form all the numbers in their natural order as a syndromes. So that's the first step of making the error correcting code equations, yes. So basically you make such a table, and then we are going to derive some equations from this table. Let us start with first equation, yes. Basically the idea is that each column of this syndrome will be one equation. So here we have first column, yes, and we are going to make equation by weighting, taking a weight, yes, this syndrome column with this code word bit. Yes, so basically these are code word symbols. We haven't yet assigned which of them are information, which of them are control. It's not really important right now. The fact that matters is that there are total 7 of such symbols, starting from A1 and going up to A7. So we take only those symbols into our equation and add them up together, which has 1 in the syndrome. So that is for the first column, A1 has 0, we don't take A1. A2 is 0, we don't take A2. A3 is 0, we don't take A3. But A4, A5, A6, and A7 all have 1s, so we take them into the equation, add them up together, and set them equal to 0. So that is the first equation, coding equation, yes, which will be used to calculate the control symbols. So basically what we do is actually take the symbol A1 multiplied with 0 plus A2 multiplied with 0 plus A3 multiplied with 0 plus A4 multiplied with 1 and so forth. Yes, so we multiply symbol with syndrome at the specific line. Yes. Similarly, we are going to make next equation. So next equation excludes A1, excludes A4, and excludes A5 because they have zeros in the second column. And accordingly, we only choose A2, A3, A6, A7. So you can see that control symbols are actually produced as the XOR sums of specific symbols specific. So we don't add all of them. We only choose 4 out of 7 and add them. And for each equation, we choose different for. So for the first equation, we chose A4, A5, A6, A7. For the second equation, we choose A2, A3, A6, and A7, and we have strict logic in choosing them. And for the third equation, accordingly, we are going to choose A1, A3, A5, A7. So we can summarize that as a set of equations which we have produced by choosing correct symbols. Yes, so this is basically a law how we make these coding equations. And now we have actually these set of equations which we can use to find control symbols. However, we haven't selected yet these control symbols. And now comes the important part of why do we choose as control symbols positions where we have powers of 2. Basically, because we need to find in each equation an element which is present only in this equation. So for the first equation, that would be A4, because we don't have A4 in second equation, and we don't have A4 in the third equation. We cannot choose A5 because A5 is present here. We cannot choose A6 because A6 is also present here. And likewise, A7 is present in all three equations. We need to choose this symbol only which is present in a single equation. And it happens so that the logic how we form this equation is based on this syndrome. Yes. And for this to be true, the syndrome needs to have only one symbol 1 in all these three, which is actually power of 2. Yes, always. And this one. So it's then settled. We use these symbols as control symbols. So basically we say that A1 is going to be, so where was that table? Yes, A1 is going to be, yes, here they are marked, by the way. Yes, so A1 is going to be E1, A2 is going to be E2, and A4 is going to be accordingly E3. Then symbol A3 is going to be C1, symbol A5 is going to be C2, and the symbol symbol A6 is going to be C3, and symbol A7 is going to be C4. And that's how we get to our non-systematic code word notation. Yes, that's actually coming from these equations. And well, we basically just derived it ourselves. Yes, so these are coding equations, and accordingly, red color denotes control symbols in non-systematic. If you are having a systematic code as your task in your course project, then you still make non-systematic exactly the same way. You still get exactly the same equations. You just rearrange symbols on paper by writing them in different order. For example, in our particular case, like this. 7, A1, A2, and A4, because you can always just rearrange your array in any programming language. In schematics, you can reconnect wires in a different way. So basically, it's not a problem, yes, to change the order of the symbols. So this is the set of equations for non-systematic code. And for that matter, for systematic code, you make the same set of equations. So you make this step in both cases, both for non-systematic and for systematic code. It will not be any difference, yes? So here you can see old notations, A1, A2, A3, up to A7. And here you can see well, we can say differentiated notations where we denote control symbols with E symbols and information symbols with C symbols, yes? And accordingly, the equation in this form will look like this. So considering that C symbols are given to us, yes, for example, C1 is 1, C2 is 0, C3 is 1 and C4 is 0, just an example of information which is sent. We can calculate control symbols now and accordingly make a code word. So, example, yes, here C1 is 1, C2 is 0, C3 is 1, and C4 is 0. That is our information part of the message which we send. Now we need to find control symbols. What we do is just substitute according values into these equations and we get control symbols. E1 is 1, E2 is 0, E3 is 1. We put them into their positions and that's how we got our code word. And this is legit allowed code word. Yes. We'll test that on the next pair today after a short break, because we need also decoding equations, yes? And well, actually, we'll talk a little, well, yes, we'll talk about this matrix after the break. Let us make a break of 15 minutes and we continue at 9:40 with decoding accordingly and matrices, yes, as well. So see you in 15 minutes, and for now we are having a short break.